Next chapter, vectors. Now, we have seen how to locate a point in a two-dimensional plane with respect to its distance from the reference axis. In three-dimensional space, we identify a point with respect to the distances from three reference planes. So, what are these planes? We take two planes perpendicular to each other. The intersection of these two perpendicular planes is a straight line. Let's take another plane perpendicular to both the existing planes. At the intersection of the two planes, we get three lines mutually perpendicular to each other. These lines are called the axes X, Y, and Z. All meet at the origin O. The plane formed by the X and Y axis is called the XY plane. Equally, the plane formed by the Y and Z axis is called the YZ plane. And the plane formed by the Z and X planes is called the ZX plane. The three planes divide space into 8 octanes. Any point in space is represented with the help of the distances it measures with respect to the planes. These distances give the coordinates of the point. For example, a point P in space will have the coordinates x, y, z. Each coordinate individually indicates the shortest distance of the point parallel to the corresponding plane. X is the distance along or parallel to the x-axis. Y is the distance parallel to the y-axis. And the z-coordinate is the distance parallel to the z-axis. The origin has coordinates 0, 0, 0. And so with that knowledge, it is easy to locate a point in space using its coordinates. Given a point P, drop a perpendicular on the XY plane to meet the plane at Q. Drop another perpendicular to the XZ plane to meet the plane at point R. OR is the X coordinate, RQ the Y coordinate, and PQ the Z coordinate. To locate a point when given the coordinates, we simply reverse the process. Any point lying on the x-axis will have the coordinates as x, 0, 0. For instance, if it's at a distance 6 units from the origin, it will have the coordinates 6, 0, 0. A point on the y-axis will have the coordinates 0, y, 0, and a point on the z-axis will have the coordinates 0, 0, z. Any point on the xy plane will have coordinates of the form x, y, 0, like this point. Any point on the yz plane will have the coordinates of the form 0, y, z. And on the zx plane, it will have the form x0, z. Next, column vectors in 2 and 3 dimensions. Now, vectors written in this form xy are called column vectors, where x is the horizontal displacement and y is the vertical displacement from a given point. For example, in the Cartesian plane, the column vector PQ, where point P is 2, 3 and Q is 5, 7, is given by PQ is equal to OQ minus OP, and that is 5, 7 minus 2, 3, and that gives us 3, 4. And therefore, the components of the column vector PQ are 3 units along the x-axis and 4 units parallel to the y-axis. Equally, column vectors in 3 dimensions are written in the form x, y, z, where x is the displacement along the x-axis, y is the displacement in the direction of the y-axis, and z is the displacement in the direction of the z-axis. And so, for example, the position vectors of points A, 1, 2, 3, and B, 6, 5, 4 are OA is equal to 1, 2, 3, and OB is equal to 6, 5, 4. The column vector AB is given by OB minus OA, which is equal to 6, 5, 4 minus 1, 2, 3, and that gives us 5, 3, 1. Operations on vectors. Now, operations on vectors in 3 dimensions are done in the same way as in the 2-dimensional vectors. And so, RS is equal to 264. Then 2PQ is equal to 2 times 1, 2, 3, which is equal to 246. A half RS is equal to a half into 264, and that gives us 132. PQ plus RS is equal to 123 plus 264, and that gives us 387. For example, find the column vector representing vector Mn if the coordinates of M and N are 2, 3, 4 and 4, 5, 7 respectively. The position vector of point M is OM is equal to 2, 3, 4, and the position vector of point N is ON is equal to 4, 5, 7. MN is equal to ON minus ON, that is 4, 5, 7 minus 2, 3, 4, and that gives us 2, 2, 3. The vector is denoted using small letters. For example, OA is equal to A, OB is equal to B, OC is equal to C, and so on and so on. Next, unit vectors. Now, a unit vector is a vector whose magnitude is equal to 1. In the 2-dimensional Cartesian plane, there are 2 unit vectors, I and J, which represent points I, 1, 0, and J, 0, 1 respectively. The position vector of I is written as I is equal to 1, 0, and the position vector of J is written as J is equal to 0, 1. Vector I is in the positive direction of the x-axis, and J is in the positive direction of the y-axis. Given a point A, 3, 2, its position vector OA can be given in terms of I and J. Point A, 3, 2 is 3 units from O parallel to the x-axis and 2 units from O parallel to the y-axis. The position vector of point A is OA is equal to 3, 2. But OA is equal to ON plus NA, that is 3, 0 plus 0, 2. That is also equal to 3 into 1, 0 plus 2 into 0, 1. But remember, I is equal to 1, 0 and J is equal to 0, 1. And therefore OA is equal to 3I plus 2J. Similarly, if the coordinates of point B are 5, 8, then OB is equal to 5I plus 8J. In a position vector, the x-coordinate is a coefficient of I and the y-coordinate is a coefficient of J. And so the position vector of Q, 6 minus 2, will be 6I minus 2J. In the 3-dimensional Cartesian plane, there are 3 unit vectors, I, J, and K, that represent points I, 1, 0, 0, J, 0, 1, 0, and K, 0, 0, 1, respectively. The position vector of I is I is equal to 1, 0, 0. The position vector of J is equal to 0, 1, 0. And the position vector of K is equal to 0, 0, 1. Vector I is in the positive direction of the x-axis, J is in the positive direction of the y-axis, and K in the positive direction of the z-axis. And so given point P, whose coordinates are 2, 3, 4, its position vector OP can be given in terms of I, J, and K as OP is equal to 2, 3, 4, which is equal to 2, 0, 0 plus 0, 3, 0 plus 0, 0, 4. That is also equal to 2 into 1, 0, 0 plus 3 into 0, 1, 0 plus 4 into 0, 0, 1. But remember, 1, 0, 0 is I, 0, 1, 0 is J, and 0, 0, 1 is K. And therefore this can be written as 2I plus 3J plus 4K. And therefore, given a point S whose position vector is OS is equal to ABC, it can be expressed in terms of I, J, and K as OS is equal to AI plus BJ plus CK. The coefficients of I, J, and K are the x-coordinate, the y-coordinate, and the z-coordinate respectively. Next, the magnitude of a vector. Now, the magnitude or modulus of a vector is the length of the vector. For example, vector OM is equal to 3, 4 is represented on the figure on your screen. OMN is a right-angled triangle. According to Pythagoras' theorem, OM squared is equal to ON squared plus NM squared. And therefore OM is equal to ON squared plus NM squared, square root of whole. The magnitude of OM, denoted by OM sandwiched between two vertical lines, is given by 3 squared plus 4 squared, square root of whole. That is equal to the square root of 25, and that gives us 5 units. In general, the magnitude of a vector A is equal to xy is given by modulus of A is equal to x squared plus y squared, the square root of whole. In the same way, we can find the magnitude of a vector in three-dimensional system. For example, the vector OP is equal to 2, 3, 4 is represented as shown on your screen. The magnitude of OP is equal to 2 squared plus 3 squared plus 4 squared, and that gives us the square root of 29, which is equal to 5.385, correct to 4 significant figures. In general, the magnitude of a vector B is equal to xyz is given by modulus of B is equal to x squared plus y squared plus z squared, square root of whole. For example, find the magnitude of the following vectors. A, P is equal to minus 3, 4. B, Q is equal to minus 3I plus 2J plus 5K. In the solution, A, P is equal to minus 3, 4. And so we shall have minus 3 squared plus 4 squared, square root of whole. That gives us 9 plus 16, 25, and the square root of 25 is 5. And so the modulus of P is 5 units. B, Q is equal to minus 3I plus 2J plus 5K. That can be written as Q is equal to minus 3 2, 5. And so the modulus of Q is equal to minus 3 squared plus 2 squared plus 5 squared. That gives us 9 plus 4 plus 25, that is square root of 38. And correct to 4 significant figures, that will give us 6.164 units. Next, parallel vectors. Consider these two vectors AB and PQ. AB is equal to B minus A, that is 6, 5 minus 3, 2, which gives us 3, 3. PQ, on the other hand, is equal to Q minus B, that is 10, 6 minus 4, 0, giving us 6, 6. Looking at these two, PQ is twice as big as AB. We say PQ is equal to 2AB. Thus, AB is a multiple of PQ. Looking at the vectors, they have the same gradient and are therefore parallel. In general, if a vector is a multiple of another, then the two vectors are parallel. That is, if A is equal to KB, where K is a scalar, which could be a fraction or a whole number, then A is parallel to B, also written as A parallel to B. For example, if P is equal to 3, 2 and Q is equal to 9, 6, looking at the two, if you multiply P times 3, then it will give us Q, and therefore we say Q is equal to 3P, and therefore P and Q are parallel vectors. An example, given A is equal to 3I minus J plus 4K and B is equal to 2I minus 2 over 3J plus 8 over 3K, show that A is parallel to B. A is equal to 3 minus 1, 4 and B is equal to 2 minus 2 over 3, 8 over 3. Taking a factor R, let us test whether the two are factors of each other. AR is equal to B. Let's try with the x coordinates. We equate the x coordinate of A and the x coordinate of B. 3R is equal to 2. Dividing both sides by 3, R is equal to 2 over 3. So the multiplying factor is 2 over 3. Let's test whether it's consistent with the other coordinates. We take Z. 4R is equal to 8 over 3. To remain with R, we multiply both sides by 1 over 4. And so we shall get R is equal to 2 over 3. And so we say B is equal to 2 over 3A. And therefore A and B are parallel. Next, collinear points. Now consider the points P, Q and R. These 3 points can be joined by a single straight line. If points lie on the same straight line, they are said to be collinear. From this figure, PQ is equal to Q minus P. That is 2, 5 minus 1, 3, and that gives us 1, 2. And therefore vector PQ is equal to 1, 2. QR, on the other hand, is equal to R minus Q. That is 4, 9 minus 2, 5, and that gives us 2, 4. Therefore vector QR is equal to 2, 4. From this, we can see that QR is equal to 2PQ, and therefore PQ and QR are parallel. Notice also, Q is a common point. We therefore say the points P, Q and R are collinear. In general, points are collinear if they have 1. Parallel vectors and 2. a common point. Next, midpoints of vectors. Now consider points A, x1, y1 and B, x2, y2. Previously, we saw that the midpoint M of vector AB will have coordinates M, x1 plus x2 over 2, y1 plus y2 over 2. Equally, in three-dimensional vectors, the midpoint of vector AB will have coordinates M, x1 plus x2 over 2, y1 plus y2 over 2, z1 plus z2 over 2. For example, find the midpoint M of PQ if P is 256 and Q is 472. M will have coordinates 2 plus 4 over 2, 5 plus 7 over 2, 6 plus 2 over 2, and that is M 364. Next, proportional division of lines. Now, line AB is divided into 4 equal parts. C, D, and E are points on the line such that AC is equal to CD and is equal to ED, which is equal to EB. From the line, AC is a quarter of AB, AD is a half AB, and AE is 3/4 AB. In ratio form, C divides AB internally in the ratio AC to CB is equal to 1:3, or BC to CA is equal to 3:1. D divides the line internally in the ratio AD to DB is equal to 2:2, or 1:1. A point divides a line AB internally if it lies in between A and B. External division of a line. Line AP is divided into 7 equal parts. AB is divided externally by P in the ratio AP to PB is equal to 7 to -3, or -7 to 3. Equally, Q divides AB externally in the ratio AQ to QB is equal to 5 to -1, or -5 to 1. In the case of internal divisions, the direction of the divisions is positive, while in the case of external division, the divisions are in the opposite direction. Next, the ratio theorem. Now consider the figure on your screen. The position vectors of A and B with respect to O are A and B respectively. Given that AP to PB is equal to 1:2, we can find the position vector OP in terms of A and B. From this figure, if we want to move from A to B, we don't move along that straight line, we have to move along the vector lines. So to go from A to B, we move AO and then OB. Therefore, we say AB is equal to AO plus OB. That will be equal to minus A, because we are moving in the opposite direction, minus A plus B. We can write that as B minus A. Now, from the ratio, AP is equal to 1/3 of AB. I hope you can see that. You can also say BP is equal to 2/3 BA. Now, let's find OP. Now, to move from O to P, you can take the straight path, but then we do not know the vector OP. Luckily, in vectors, the path followed does not matter. What matters is the initial and the final position. And so to move from O to P, you can take 2 paths. either OA then AP, or OB and then BP. Let's try OA and then AP. So we say OP is equal to OA plus AP. Then we shall have A plus AP is a third of AB, and we had already calculated AB. So we shall have A plus a third into B minus A. If we open that bracket, we'll have A plus a third B minus a third A. If we complete that, we'll get 2 over 3A plus a third B. And that is equal to 2A plus B over 3. In general, the position vector of a point P dividing a straight line AB in the ratio n to m is given by OP is equal to P and is equal to MA plus NB over M plus N, and this is called the ratio theorem. Now, someone may wonder, suppose we had taken the path OB and then BP, would we still end with the same answer? Trust me, we would. Let's try that. OB plus BP will be equal to B plus 2 over 3 BA. Notice now we are moving from B towards A. The direction has reversed. Now we have already calculated AB and found it's B minus A. Notice now that BA is the opposite of AB, that is minus AB. And so if we substitute that, BA will be equal to minus vector B minus vector A. If you open that bracket, we shall have minus times B is minus B, minus times minus A is plus vector A. If we rearrange that, then we shall have A minus B. So let's use that in our calculation now. OB plus BP will therefore be vector B plus 2 over 3 vector BA. We've calculated BA now and found it's A minus B. We open that bracket. Vector B plus 2 over 3 vector A minus 2 over 3 vector B. That gives us B minus 2 over 3 vector B will give us a third vector B plus 2 over 3 vector A. Factorizing that, we can get 1 over 3 into 2A plus B. And that will give us 2 vector A plus B over 3, the same answer. The only danger with following the second method is the involvement of negatives, which are likely to introduce confusion if you are not very careful. We take an example. In this figure, find the position vector of n in terms of A and B. Now, according to this figure, n divides AB in the ratio 2 to 3. According to the ratio theorem, ON is equal to vector n and is equal to m, in this case will be 3, so we have 3A plus n will be 2, that's 2B over 3 plus 2 is 5. If you use the long method, you first calculate AB, and AB is equal to AO plus OB, and that is minus A plus B. We rewrite that to be vector B minus vector A. ON is equal to OA plus AN, that is OA plus 2 over 5 AB. But then AB is equal to B minus A. And so ON is equal to vector A plus 2 over 5 into B minus A. That gives us A plus 2 over 5 vector B minus 2 over 5 vector A. Simplifying that, we shall have 3 over 5 vector A plus 2 over 5 vector B, which can be written as 1 over 5 into 3 vector A plus 2 vector B, and we can have it as 3A plus 2b over 5.
One of the wonderful things about mathematics, I think, is that people are impressed. It's often seen as a very hard subject, and so if you've done math, it's often treated as an entrance requirement, as a credential to do lots of other things. And so one idea is that for example, some MBA programs, the only thing they require going into it is a good, solid math understanding. They can teach you all the business. They just can't teach you the math fast enough. And so I think that math, aside from obvious careers that require math, if you're going to go work in a department that does operations research or something like that, they'll want people with specific skills in mathematics. But math is often seen as a filter or as a screen for many, many other disciplines. And so I guess what I'm trying to say is you can think broad, because math actually is a solid preparation. It's a good credential to go into lots of different fields that people often don't consider at the beginning.